Hello everyone, welcome to the chemistry channel. So today we're going to be talking about two very mathematical topics. There's not going to be too much concepts that we are going to be discussing. In fact, barely any. We're just going to be talking about different mathematical methods that you can use in order to find the empirical formula of an unknown substance or unknown compound. So in this video, we're going to be talking about calculating the empirical formulas from chemical analysis and then using those ideas to discuss combustion analysis. So before we get into the bulk of the video, let's just do a quick review. So the empirical formula of something is the formula that shows the relative ratios of each atom in a chemical formula. So for example, if we had glucose here, which is C6H12O6. This represents the molecular formula. And in order to find the empirical formula, you divide the entire compound by the greatest common factor, which is 6, and then you get the empirical formula, which tells you the relative ratios. For example, this empirical formula tells you that there's 2 hydrogens for every carbon, 2 hydrogens for every oxygen, and 1 carbon for every oxygen. If you are at all confused about empirical formulas and molecular formulas, I encourage you to go back to one of my previous lectures where I go into great length about what empirical formulas and molecular formulas are. So the one tiny new concept that I want to very quickly discuss is percent composition. Now, percent composition is probably something you've all seen either from high school or you're just familiar with it. Well, it's a very easy thing to understand. All percent composition is basically telling you how much of your sample is made up of a particular element. So percent composition is therefore equal to the mass of the element within the compound over the mass of the entire compound times 100%. So for example, if you had a 100-gram compound, so 100-gram compound, this means compound, and let's say 12% of the compound is hydrogen, how many grams of hydrogen is in this compound? Well, all you would have to do is take 0.12, because that is the percentage in decimal form, so 0.12 times 100 grams, and when you multiply this together, you get 12 grams of hydrogen. Okay, so that's all percent composition is basically telling you. How much of a particular element makes up the compound. So with that, we can now get into our real topics for today. So in this video, I'm going to be doing 2 practice problems in order to demonstrate these particular mathematical methods. So the first topic deals with using chemical analysis to determine the empirical formula. So let's say that an unknown compound was analyzed and found to contain these percent compositions. So the compound contains 62.07% carbon, 10.34% hydrogen, and 27.49% oxygen. Determine the empirical formula using these percent compositions, and down here I have the particular atomic masses that I want you to the particular molar masses that I want you to use. So if you want to try this for yourself, I encourage you to do so. However, if you just want to watch in this video, you are free to do that as well. So with that, let's go through this together. So the first thing that I want to do is to assume that we have 100 grams of substance. So assume we have 100 grams of, let's get rid of this O. Okay, so assume we have 100 grams of the compound. So that is the first step. So assume we have 100 grams of compound. So from this we see that we have 62.07 grams of carbon, 10.34 grams of hydrogen, and then 27.49 grams of oxygen. And if you don't understand why, I'll just do a quick math and then a quick mathematical expression just to show you. So in this case, if we have our percent composition, which is equal to the mass of the element in the compound, so that's what that symbolizes, over the mass of the compound times 100%. In order to find out the mass of the particular element, what you do is you take the percent composition. So in this case, you take, let's just do oxygen, so 27.49%. The mass of the compound is 100 grams. And then you multiply that by 100%, and then you have the mass of the element. So in order to do this, you multiply 100 grams by 27.49, and this would equal 2749% by grams, because that's just conserving units, because you multiplied grams by percentage, so this would be grams times percentage. So in order to find the mass of the element, you divide by 100%, allowing percent to cancel out. So let's just use a different color. And then that would give you your grams. So if you divide this by 100, you get 27.49 grams is equal to the mass of oxygen. So that's why assuming 100 grams makes the math really easy, because it just allows you to directly convert the percentage into a mass. So that's why it's very easy to do an assumed mass of 100 grams. So let's just get rid of all this. Okay. All right. So now that we have the grams of each substance, of each element, let us convert these into moles. So the next step is to convert the mass into moles. Okay? So the first one that we're going to do is carbon, because we have this first. In order to convert this to moles, you take 62.07 grams of carbon times 1 over 12.01 grams, because this is the molar mass. So let's put moles here. So there are 12.01 grams per mole of carbon. And when you plug this into your calculator, you will get, so let's do that, 62.07 divided by 12.01 will equal 5.168. 2 moles. Our overall estimate should have our overall products should have 4 sig figs as well. So let's just show the canceling out here. So grams cancels out, allowing you to get moles of carbon. And now you repeat this for the other elements. So you have your hydrogen. So 10.34 grams of hydrogen over the mole is over the inverse of the molar mass of hydrogen. So 1.01 grams of hydrogen per, let's actually get rid of the hydrogen there. Grams per 1 mole of hydrogen. And then that would equal, so let's put that in our calculator as well. So 10.34 divided by 1.01 is equal to 10.23. And just to keep the this correct number of sig figs, I'll just put a little underline under the 2 because we only have 3 sig figs here. So we'll do 3, 8 moles of hydrogen. Okay? So now what we can do is do the same thing for oxygen. So 27.59 grams of oxygen times the inverse of the molar mass of oxygen, which is equal to 16.00 grams per 1 mole of oxygen. This would equal 1.724 moles of oxygen. Okay? All right, so now that we have all the moles of each element, what do we do? Well, the next step is to divide by the smallest mole value in order to get the simplest mole ratio. So in other words, we divide every single number by the element that has the lowest number of moles. So in this case, we'd use oxygen. So in this case, we divide 1.724 moles from every single number here. So let's start with carbon. So with carbon, we had 5.1682 moles. And then we had 1.724 moles of oxygen. Now let's make sure we have the correct number of sig figs. So in this case, we have 4 up here and 4 down here. So when you plug this into your calculator, you will get, so let's do this, so 5.1682 divided by 1.724, you will get around 2.998. So we can't have this in our final chemical formula, so we round up because this is so close to 3, we call this 3. So you have 3 carbons. All right, so now let's move down to hydrogen. So hydrogen would be 10.238 moles over 1.724 moles. And when you put that in your calculator, you would get, let's see here, 1.724. You would get 5.939 because we also have, in this case, you would have 3 sig figs. Okay, so this would actually be 9.4 if you're going to count for the sig figs. So let's put the 4 here. 5.94. So we round this up as well because this is super close to 6. We say 6 hydrogens. And of course, if you divide oxygen by itself, so 1.724 over 1.724 equals 1 oxygen. Therefore, your empirical formula is C3H6O. And that is your answer. So that's the process that you can use for this type of problem here. Okay? So now let's get into combustion analysis. So combustion analysis uses combustion reactions in order to determine empirical formulas. So it uses combustion reactions in order to determine empirical formulas. So it will follow this general reaction. So CX HYOZ plus O2 goes to H2O and CO2. Okay? Now, of course, this is not balanced. All I'm trying to show you here is that in combustion analysis, you'll often take a hydrocarbon with oxygen in it, and you'll react it with oxygen, burn it, and see how many moles of water and carbon dioxide you form. And from that, you can determine the empirical formula of your sample. So in this case, your hydrocarbon. So an unknown hydrocarbon contains carbon, hydrogen, and oxygen. If 0.765 grams of this hydrocarbon forms 0.918 grams of water and 1.683 grams of carbon dioxide, what is the empirical formula of the unknown hydrocarbon? And here we have the different molar masses that I want you to use. So in order to do these types of problems, there's a general procedure that you have to follow. The first is to determine the mass of each element in the compound. So this is the first step that we are going to do. So we want to find out how many grams of carbon, hydrogen, and oxygen are in this unknown hydrocarbon. So we'll start off with carbon. So if we look at our general equation here, so this is our general combustion analysis equation, you'll see that a combustion reaction makes both water and carbon dioxide. So the easiest thing to start off with is carbon, and that's because any carbon dioxide produced has to be due to the carbon from the particular compound. So the first thing that you should do is find out how many grams of carbon were in the particular compound. So let's do that. So if you have 1.683 grams of CO2 formed, and we know that the molar mass of CO2 is 44 points. Let's just add it. So if you don't know how to add this, what you do is you add the molar mass of the two oxygens to the carbon. So 12.01 plus 16 plus 16. And that equals 44.01 grams per 1 mole of CO2. Now, per 1 mole of CO2, we have 1 mole of carbon, right? Because there is 1 carbon and 1 molecule of CO2, in 1 compound of CO2. So then what we do is we have to convert these moles of carbon to grams of carbon, and we can do that by multiplying this by the molar mass. So per 1 mole of carbon, you have 12.01 grams. And when you plug this in your calculator, you get 0.4593 grams of carbon. Okay, so we have our carbon. Next, we can do hydrogen, because in this case, we know how much. Let's go back to our general equation. So in the combustion reaction, we have water being formed. So if your reaction is nicely isolated, all of the hydrogen produced, all the water produced, and the hydrogen within that water produced will be due to the hydrogen in the sample. So let's take the amount of hydrogen. So in this case, 0.918 grams of H2O. And now the molar mass of water, you calculate it in the same way as you did carbon dioxide. And if you are confused about how to calculate these, I go over it in one of my previous videos. I think when I first introduced empirical versus molecular formula. So go check that out. So the molar mass of water is 18.02 grams per 1 mole of H2O. And now per mole of H2O, there is 2 moles of hydrogen, and per 1 mole of hydrogen, you have 1.01 grams. So this allows you to find the amount of grams of hydrogen in the sample. So in this case, you would get 0.1029 grams of hydrogen. Now, if you want to conserve the amount of sig figs, so in this case, 3, just put a little underline under the 2. Keep that 9 there so you don't get rounding errors later on. So the last thing is to find the mass of oxygen. This is the trickiest part. However, there is a particular formula you can use. So in this case, if you have the mass of oxygen is equal to the mass of the sample minus the mass of hydrogen minus the mass of carbon. And that is the equation you use. And why do you think that is? Well, if you think about it, if you take your sample mass and you know the amount of carbon in it and the amount of hydrogen in it, all you have to do is subtract those two numbers from the total mass in order to get the amount of oxygen in there. So it actually makes a lot of sense that way. So let's do that. So our total mass was 0.765 grams. And then we'll subtract our mass of carbon, which was 0.4593 grams, and our mass of hydrogen was 0.1029 grams. And let's put our sig figs there. Our overall result will have 3 sig figs, and when you put this in your calculator, you should get something around 0.2028 grams, and I'll put a little underline indicating we have 3 sig figs. So now we have the mass of oxygen, the mass of hydrogen, and the mass of carbon. So now what do we do with it? Well, what we do with it is we now have to convert all of these masses into moles. So let's do that. So let's first do this for carbon. So let's actually write that step down. So convert all masses into moles. So let's do that for each one. So we have 0.4593 grams of carbon times the inverse of the molar mass of carbon, so 12.01 grams per 1 mole of carbon. And this would give you 0.03824 moles of carbon. So now let's do the same thing for hydrogen. So we had 0.102, so put that underline there, grams of hydrogen. We can multiply that by the molar mass, so 1.01 grams of hydrogen. Oops, let's get rid of that hydrogen. Should go on the top, not the bottom. 1.01 grams per 1 mole of hydrogen. So when you plug that in your calculator, you should get around 0.1019 grams of moles of hydrogen. So let's change that too. Sorry about that. Did it a little too fast there. So let's underline that we should have 2 sig figs, just in case. And then the last one is moles of oxygen, where we had 0.2028 grams of oxygen. So put your little underline under the 2. And then you get 16.00 grams per 1 mole of oxygen, which is then equal to 0.01268 moles of oxygen, and then we'll just put our little underline under the 6. So next, we could repeat the step that we talked about in the first example. So when we divide by the smallest mole value in order to get the simplest mole ratio. So in this case, we're going to repeat that step. So let's write that step. So this is the third step that you do to solve all combustion analysis problems. And let's write that down. So you divide by the smallest mole value to get the simplest mole ratio. So in this case, we do, let's see here, we're going to use the oxygen, the amount of moles in oxygen. So let's just quickly do this. So let's do carbon first. So carbon, we had 0.03824 moles. And then for oxygen, we had 0.01268 moles. And then let's just put our little hash under here so we know how many sig figs to use. So when you put this in your calculator, you will get, so I'm putting it in right now, you will get 3.02. Now we round this down because this is way closer to 3. So in this case, we have 3 carbons. So we have 3 carbons. So we got carbons down. So let's do hydrogens now. So 0.1019 moles. So let's put a little hash under the 1. Divide that by 0.01268 moles. And then when you put that all together, let's put that in our calculator. So 0.019 divided by 0.01268 gives you 8.04. And you round this down because this is closer to 8, so you get 8 hydrogens. And then oxygen, when you divide 0.1268 from 0.01268, you get 1 oxygen, of course. So therefore, our empirical formula is C3H8O. And therefore, we use combustion analysis to successfully find the empirical formula. So guys, that is it for today. I hope my descriptions made sense to you. And just one more thing I would like to say is that for all combustion analysis problems, you can use these 3 steps. So for example, if you're trying to find the, if they don't give you the amount of CO2 produced, you can use the same thing. So no matter what unknowns you get, you can use this same general process, these same 3 steps. So the best way to master these types of concepts are to, of course, do practice problems. So I encourage you to go into your general chemistry textbook or your professor's homework that they assigned you and to just practice these problems on your own. And that way you'll get really good and really quick at them. So I thank you for watching, guys, and hope to see you next time.